Okay, shall we start? Let's try it this way. So, shall we start, everybody? Hi. So, just the quick update for the project. Please, if you have not done, I think those who have submitted their names, you should have right now a group. So on Kirkus, so there should be a group assigned to you. Everybody in the group. If it's not the case, you can just follow it up. And those who have not yet submitted, please submit your group so you can just submit the proposal. And yeah, that's about the project. And then let's get back to the lecture. So we ended up talking about the classification problem. So we talked about the binary classification. There in the binary classification, we wanted to just do one very simple task, and that was that we had a bunch of handwritten numbers in the form of images. The images are 28 by 28. And what we want to do, we want to just look at the image and say whether it is the handwritten 2 or it's something else, right? So this was the idea, and what did we do? We just started doing the basic thing. So this was our data set, if you remember. So this x is basically your pixel vector, so including all those 28 by 28 image pixels. And then VB, it was a binary label, meaning that it's either 1 or 0. It's 1 when we have a handwritten 2. It's going to be 0 if it's something else. And then we started to think about the one simple architecture. This was the architecture. So we just talked about how many parameters do we have here. The idea was that we have just the input, and then we have 2 hidden layers, and finally we get the output through one particular perceptron. And we decided to use perceptron because we wanted to have the output 1 or 0. We had no other choice, right? So we did this with the perceptron, but the thing that we noticed was that when we want to just backpropagate over this architecture, so this was the computation graph, when we want to backpropagate over this guy, we're going to get into trouble. So we had 2 main troubles. What are the troubles? Activation function of the output and the loss. Great, right? So the loss function cannot be differentiated, so you cannot compute the derivative of this one. And also the step function, they do not have derivative, right? And then if you just write down the backpropagation, it doesn't work, right? Because this L dot does not exist. Even if you think of constant function going to be 0, this S dot is also always 0. So basically nothing is going to backpropagate over this whole architecture. So that was the whole issue. So we talked about this, and then we came up with the idea of solving the problem using a sigmoid function. We said like a step function is not having derivative. It doesn't have gradients. We want something looking like step function, but having gradient, right? And then the best choice came to our mind was the sigmoid function. The sigmoid function is somehow smooth, going from 0 almost to almost 1. And it has gradient. Like at every single point, you can compute the derivative, and it's not 0, right? So it's a very good function, so maybe we can replace it. We just did this replacement, but then we came up with another issue. What was the next issue? The output of the neural network is not 0 or 1 anymore. It's a number. It's a scalar between 0 and 1. And then now, how we can interpret this as a kind of label. So it was not label anymore. We said maybe we can interpret this to be a probability, right? So this is just telling us what is the chance of the label being 1. And then if it is very high, then more than half, then this is more likely for our input image to be a handwritten 2. If it is smaller than half, then more likely it is not a handwritten 2, right? So this was the idea. We just translated or interpreted this number to be a probability. But then the issue was that we wanted to just compare this with the ground truth. And the ground truth is again 1 or 0, right? So how did we resolve this? We again looked at the true label as a probability, right? We said, okay, the true label is also probability because if the label is 1, we can say that the true label is 1 with probability 1. If the label is 0, we can again say the true label is 1 with probability 0, which means that it is 0 with probability 1, right? It's the same thing. So we could in general say that any true label given to us is 1 with probability v, and this v is either 1 or 0, right? And now the thing is that we have two probabilities. One of them is the output of the neural network. The other one is the ground truth that we have it. And we want to compare these two against each other. And how can we come up with the loss function? So the first loss function we talked about was the classic square loss, which was just get the two numbers, subtract them, make them square. It's going to compute the loss because basically you want here the output of your neural network, the red guy, to be exactly as the true label v, right? So this is going to make your loss minimum, and this is a good thing, right? But we said this is not the best idea, even though this is differentiable, so we don't have any problem. Now we can backpropagate over our architecture, but this is not the best idea. And the reason was that it was not, strict enough in penalizing getting out of the region, right? And the better idea was to just think about two probabilities and write down the cross entropy. So the cross entropy, we defined it in this form. So this was the cross entropy, which is basically the logarithm of 1 over the probability of the label, right? So if the label is 1, then it's going to be 1 over y3, because y3 is the chance of being 1. If the label is 0, then it's going to be a logarithm of 1 over 1 minus y3, which is basically the chance of being 0, right? So this was the idea of cross entropy, and we talked about this, that this guy is essentially having a better gradient, because the mean squared error is going to just drop smooth from 0 to, from 1 to 0, but the other one is really just penalizing very harshly. So it's just pushing our neural network to just, if our neural network just gives us very bad estimate, very bad output, like a bad chance, like the label is 1, but it's giving a probability close to 0, which is not the case, then the loss function in this case is going to give a very, very high penalty to it. And this means that the gradient is going to be much larger, and then when you are backpropagating, most probably in your next update, you're going to have your probability change much more, right? And this is the key point of this cross entropy. So this was the idea of cross entropy, and once we have the cross entropy, now we can replace the loss function to be the cross entropy. We can replace here the step function with sigmoid, and now everything can backpropagate, right? Because every single of those guys exist, right? They are non-zero things most of the time, and you can't really backpropagate over that architecture, right? Okay. Cool. So this was the idea, and now the next thing is the idea of doing inference. So when we started, I told you that you always have two phases with your neural network, right? One phase is to do training, meaning that you get your architecture, you just give your data, you try to make or tune this architecture in a way that it gives you the output you want. The next thing that you should do is inference. You get a new data, you just give it to your architecture, you see the output, and out of the output you try to decide, predict, right? So now, if in this architecture I just do the training, meaning that for every label I try to make that probability close to 1 when the label is 1, and try to make it close to 0 when the probability is 0. And then I'm over by training, right? So the training has been done. Now the next thing is that I need to do inference, right? So you give me a new image, I give it to this trained neural network, and I want to look at the output, and when I get the output, I should infer from that output whether this is handwritten 2 or not. Now if I give a new image to this neural network, and it gives me as the output 0.7, what do you conclude? It's likely being handwritten 2. Why? Yes, because the probability of being 1 is more than the probability of being 0, right? Probability of being 1 is 0.7. Probability of being 0 is 1 minus this guy, which is 0.3. So 0.7 is more likely than 0.3. So this is basically the idea. So once you just pass a new image, then you're going to have Y3. This is going to describe the chance of that image being handwritten 2, right? And then out of this guy, you can basically decide whether this is, you can infer or you can conclude this is a handwritten 2 or not. So you would say, okay, if Y3 is the chance of being handwritten 2, then 1 minus Y3 is the chance of being any other handwritten number. And you basically want to make sure that you are taking the most likely output. So you're basically going to just take this as 1 or take it as handwritten 2 if your probability is more than half. If it is less than half, then you're going to take it as 0, right? So your neural network is not giving you really the label that you want, but it's giving you a sort of soft information based on which you can conclude whether it is 1 or 0. You got it? So is it clear? Right? So you're going to see it from now on. Always when we do classification, we don't work with true labels. We always work with probabilities. And the key reason exactly is the one I told you. Because with probabilities, you are just working with a kind of continuous space. You can have gradient. You can backpropagate. You can train it. If you just want to stick to the true label, like what was being done by perceptron machine, then you're going to get stuck to those issues that we had before, right? So in the phase of inference, we're going to just look at this as a probability as it is really, and then we're going to take the one which is the most likely one. Now, one question from my side. Now, we had this story, nice story, but in practice, you do know that it's not a very sophisticated test to just get an image and say whether it is handwritten 2 or not. What if I want to check whether it is handwritten? I mean, I have all possible integers, like 0, 1 till 9, one-digit integers. Okay? Say I have all of them, and now I want to just have a classification on that, like the true MNIST data set. Right? So I give you one handwritten digit, and I want the neural network to tell me whether it is handwritten 0, 1, 2 till 9. So what is your idea? I mean, for this binary one, we could do it. We just computed the chance of being 1, right? What if I want to have 10-class classification? Yeah?
We can have 10 neurons, and we assign each probability. The one with the highest probability can be.
Yeah, that's a cool thing, yeah. But if I am computing 10 probabilities, right? If you have 10 different neurons, each of them going to be something between 0 and 1, right? Yeah, it's going to be very low. Yeah, it's going to be between 0 and 1, right? And then if you sum them up, there is no need that it's going to be 1 exactly, right? So it means that if you compute the chance of being 0 and it's high, it could be that the chance of being 1 is also high, right? So, but it's not a cool idea, right? What if you ended up with the chance of 5 of them out of 10 being 0.9? This is not the best idea, but you got the intuition pretty good. So you basically need to compute the chance of every class happening, right? So this way of interpreting the classification, looking at instead of looking at the label, just looking at the chance of the label happening, can help us extending this diagram or this neural network easily to multi-class classification. So let's see how we can do it. So I told you at the very beginning that whenever you have a multi-class classification, you can do it by looking at it as a sequence of binary classifications, right? So in this problem, it means that you should, if you want to do that, you're going to say exactly like what I did. So you're going to say, is it handwritten 0 or not? If it is handwritten 0, then it's over. If it is not, then you're going to go, is it handwritten 1 or anything more than 1? So if it is okay, so if it is handwritten 1, you're going to sub. If not, you're going to go for the next one, and so on, right? But if you want to do it as a kind of hierarchical architecture, right? So it's like you have multiple neural networks, and this is too much computation, too much complexity. You don't really want it. The better idea is that we just compute the chance of every single class happening in one shot. Okay? So what can I do? I can just say that, okay, my label could be anything, say, for instance, from 0 to 9, and then I simply compute the chance of every single label happening, right? So the idea is simply that I replace that last layer into a layer which can compute the chance of all the classes in the multi-class classification problem. Okay? So let's see how we can do it. So this is our architecture, right? And now I am computing at the output 1 probability, right? But that 1 probability is not actually 1 probability. It's, to be honest, 2 probabilities, right? When I have y3, I also have 1 minus y3. So the probability of the 2 classes. Now say I have C different classes, so class 1 to class C. Okay? So if I could replace this sigmoid here with one, say, super node, a kind of big node, which gets everything from the previous layer, and then it's not just generating 1 probability for me, but 10 probabilities in one shot for me, right? So 10 numbers, all of them non-zero between 0 and 1, and when I sum them up, it's going to be exactly 1. Then this is just telling me what is the chance of every single class or the input belonging to every single of those classes, right? So I can do it. This is the idea that we call it vector neuron, or this is a kind of neuron with vector activation. Okay? So let's break it down and see how exactly this neuron looks like. So now, as you can see, this guy is again a kind of neuron, because this is like this guy, right? It's going to get lots of inputs. This also gets lots of inputs. But this one, the only difference with these guys is that every single neuron here, the classical ones which we had up to this point, every single of them is just generating one number, one scalar at the output, right? This guy is just generating a vector at the output, right? See different things all together, right? So this is the only difference, but it is at the end of the day same thing as our neuron. So as I said, this is what we call it vector activated neuron. And we can simply extend the idea of basic neuron that we have into a higher dimensional case. Meaning that assuming that this vector neuron is being fed by some input x, so x could be in general n dimensional, so it could be n different entries inside this guy. And all of them are just going inside this neuron. Then I'm going to have one, instead of one vector of weights, now I have a matrix of weights. Because this is a matrix getting this large, say, n-dimensional input, and then just transforming it into a c-dimensional vector. Okay? So it's going to compute c different values for my c different classes. All together. Okay? So I'm going to have one matrix W here. This is containing all the weights. And I have one bias. Of course, every single of them could be added with one bias as well. So I have a vector of biases, right? Everybody's clear? So what is the dimension of this matrix? Say I have 10 outputs, 10 classes, and the input to this layer is 20. What is the dimension of this matrix? 10 by 20, because it needs to get 20 inputs and going to return 10 outputs for me, right? And what is the dimension of my bias vector? It's again 10, right? The number of classes that I have, right? And then you put that number of classes instead of 10 to 1, it's going to be exactly the neuron that we had before, right? That weight matrix is going to be a weight vector. This bias is going to be a single number. And this is exactly the original artificial neuron we had it before, right? So this is just simple guy as we had before, just extended to higher dimensional, right? Now, once you compute this, once you just do the projection, so you get your n-dimensional input and you compute a c-dimensional output out of it, then you're going to activate this one. But there is one key difference here, and the difference is that you are not doing entry-wise activation anymore. It means that this function f, and the reason that I am writing it down capital now is because it is not an entry-wise function anymore. So it's not operating on every single input individually. So it's going to look at the whole calculation, whole C different calculation as a whole, and then compute a whole C new activated values for you. Okay? So every single of these guys could be depending on all of the inputs, right? And we're going to see an example right now. But you got the difference, right? Because if I replace this f to be simply one entry-wise operation, then it's going to be simply C different neurons, right? So I'm not doing it. I'm just doing the whole activation altogether. Everybody's clear? Right? Okay, so before I go on with this, guys, so let me do the first thing that I like. So I'm going to just get rid of this bias. So I don't want the bias. I put it as the first column in this matrix. And then I put 1 here. Then this expression here is going to be exactly this inner product, this product of this matrix and this vector. So I'm going to call this W as before, right? So we are not going to look at the bias anymore again, right? We always have the dummy guy with us. The dummy guy going to replace the bias place, and then we just think of it as a kind of, linear transform, and then finally one vector activation. Okay? Everybody's cool? Right? Yeah.
So the dimension of this W would be C by n plus
1, yes. Yeah. Okay, that's good. So, but don't confuse yourself with the dimensions too much. I know I say too much dimensions, but the key point is that you are just doing linear transform, right? Higher dimension. Yeah.
I think there might be some differences when we're trying to train it, because we used to let it identify whether the number is 2. But now, if we still use the same process to train it, it's not going to give us better. The weights that are set that they used to identify 2, now we want it to do a different job.
Sorry, I didn't get your question.
Yeah, because we used to let it identify some kind of binary classification.
Yes, you mean that if you use it for binary classification?
Now we want it to do some kind of multiclass classification.
Multiclass classification, right.
We cannot use the old weights to train it.
We cannot use
The old weights,
the old weights. Because you mean that here now the matrix is 2-dimensional, like it has 2 rows?
There are more rows than before.
Yes, but if you use, as we're going to see, if you use softmax, then one of the rows is essentially being deactivated, is doing nothing for you. Because one of them is always 1 minus the other one, right? And that one you don't need really to train it. So this is the reason that you see this. Like 2 to 1 doesn't change anything.
So let's say if we have a network that's able to tell whether it's 2 now, can we just expand the output layer, but not changing the layer that are?
Yeah, I got your question. So you mean that instead of using this this simple sigmoid neuron, we just use a 2-class classifier, right?
Yeah.
And then this is going to have 2 vectors of weights. One of them is for class 1, the other one is for class 0, right? So then, if you want to compute, you're going to see it. We're going to compute the softmax. And the softmax, the output, is guaranteed that the first one and second one are going to add up to 1, right?
Yeah.
Now, if you consider that one, this means that the first one is your y3, and second one is always 1 minus y3, right? And then your first row in that matrix is going to be effective. It's going to get updated when you are training. The second row is really doing nothing. So at the end of the day, you see that if you drop this, still you're going to do the same job. Okay? But what you say is totally right. Mathematically, you are doing 2 different functions in that case. But the only reason is that in the 2-dimensional case, or sorry, 2-class case, we do know that whatever the first one is, the second one is immediately computed out of it, right? But your comment is totally right. Yeah. Okay. Norse. So, any other question? Okay, no question. Then let's go with this vector activated neuron. So what we want to do, as I told you, this f function is going to just compute for us a bunch of outputs altogether from the whole input. So if you want to look at the whole computation that is happening here, we can again write it down in a form of a computation graph, right? That's going to be easier. So this is going to be whatever is given to this layer. So let's call it x for the moment. And then this guy is going to get multiplied to a bunch of weights. And this is going to compute you a vectorized z, right? It's not a number anymore. It's a vector z. And that vector z is being activated with function f. So everything is pretty much as before. The only difference here is that this function is not operating entry-wise, right? So we should pay attention to this one. That's it. But the rest of it is the same thing, only in the higher dimension. Now, the popular vector activation that we use in classification is softmax. And how do we define it? Softmax, we define it in this form. So say I have, let me just do it on the board for you. It's going to be. For simplicity, say I have, okay, it's weird. What did they do with me? Really? Okay. Say I have my vector x, okay? And say, for instance, this x is 100 dimensions. So this was x1, x2, and so on till x100. Okay? Now, when I do the transform, so when I multiply it with this weight w, and say I have 3 classes, so c equal by 3. What's going to be the vector z that I'm computing? How many entries does it have? So I have 100 inputs, and I want to end up with 3 classes. How many z do I compute here? 3, right? So this means that this matrix is going to have 3 rows, 100 columns, right? So a very, very fat matrix, right? And then this is going to get multiplied with this. This is going to give me z1, z2, z3, right? And I told you that I want to compute from this guy this vector y, which is again 3-dimensional. So it's going to be y1, y2, y3. Okay? Now, say I want to compute y1. Now, the way that softmax does it, say I want to compute y1. It's going to say that, okay, take this first guy, so I'm computing this guy, take the first guy here, and try to make it into a probability. So how you do it, you're going to put it e to power z1, okay? This is definitely non-negative, right? Can it be negative? Can this guy be negative? No, exponential function is never negative, right? But you want it to be between 0 and 1, right? So the way that you are doing it, you are going to just compute ez1 plus ez2 plus e to power z3, okay? So you're going to compute every single of them. You take every single of them into exponent, and then you sum them up here. So is it still non-negative? Nominator and denominator are both non-negative. Is it between 0 and 1? Yes, because you have this guy in nominator, and this is one of the terms in denominator. So denominator is definitely larger than this one. So it is between 0 and 1, right? Now, what's going to happen if I compute yi like this for every single I? And then I add up all of these yi's. What's going to happen? It's going to sum to 1, right? So this is a cool guy. This is a cool function, right? So this is computing a probability out of this whole vector, right? But one thing that you should pay attention is that yi, look, yi, so say for instance y1, this is depending on z1, z2, z3, right? So it's not a function of z1 anymore. You get the idea? So it's not entry-wise activation. It's not only a function of z1. It depends on z1, z2, z3, right? So this is the idea here. So softmax is going to be, if you want to compute the softmax output of one particular class, you're going to go and get the z value for your class, and you take it to the exponent. Then you divide it to the sum of exponents, exponential function, on all possible z's, right? So nominator positive, denominator positive. This is a positive number. Nominator is smaller than denominator. This is definitely between 0 and 1. And then you can simply say that if I add up all the y values, all the outputs of the softmax function for all the classes, then I'm going to have this summation. So this is the summation only running over C. So denominator is not depending on the index I am summing over. So it's going to go in nominator. And this is going to be 1, right? So this is going to add up to 1. So it means that this softmax function is looking at the whole Z and tries to convert this whole Z into a probability distribution, right? So this is the main functionality of this softmax. And pretty much in this course, we always use this one as a vector activation. So this is, I guess, the only vector activation we have in this course. Theoretically, you could have anything, but this is most of the time the thing we use here in this course. Everybody's clear what softmax is doing? So you got the idea, what do I mean by no entry-wise activation anymore? So you need to look at the whole Z to be able to compute every single output, right? Clear? Everybody's cool? Great. So that's it about the softmax. By the way, those people, I mean, anyone here had ever had anything on thermodynamics? Anyone had thermodynamic course? Yeah, you had it? So does it remind you of something, this kind of distribution? Sorry? A Boltzmann distribution, do you remember that? Yeah, no, I mean, you might not have it, right? It could be, right? Ah, okay. So you had the base. So if you just, I mean, take a bit of more advanced course on thermodynamics where you start to just look at the whole thermodynamic system as a stochastic process, then you're going to say that when every particle is going to just get into equilibrium, then they're going to look like this guy, okay? So this distribution is coming from statistical mechanics, thermodynamics, okay? It's called Boltzmann distribution. If you are interested, just search it, right? So people have made life on that, on Boltzmann distribution. So it's a kind, I mean, any distribution, most of the distributions you know are a special case of Boltzmann distribution. So softmax is pretty, say, strong sort of function. Anyways, so now that I have this particular vector activation, the only thing that I need, the only change I need to do to my network is that I take that final layer, which was a single neuron, I replace it with one vector activated neuron, and that is softmax, and then I'm going to get a bunch of probabilities, right? And now if I want to have label 1, right? So I mean, if I look at those probabilities and I see the first one is the largest one, then I'm going to say the label is 1. Okay? Everybody's clear? Any questions? Yeah, I mean, class 1, not, digit 0, right? You mean that, yeah. Okay? So, now, this is going to be the softmax, so every single body at the output is the probability of the particular class, and then the only thing that you need to do is to just forward pass your image, say you're not yet in the phase of training, so if you just forward pass it, you're going to get a bunch of probabilities, and the thing that you want is that the probability of the true class is going to be the highest, right? So this is what you want to do, and in the whole training phase, you're trying to modify those ways in a way that this is happening for your training data, right? So now, since I am a kind of obsessed person, I'm not going to leave the course here at this point, and I'm going to do the forward pass and backward pass once again with this guy, and then we're going to see what is the difference with the previous version that we had, okay? So if we want to do the forward pass, well, everything going to look like the same, right? So I'm going to get X, multiply with a matrix, get Z, activate Y. Again, multiply with a matrix, Z, activate Y. Again, multiply with a matrix. Oh, we had here a vector, right? You remember that? Now we are having a matrix. Everybody's following? So this W3 that we had, before when we had a single sigmoid at the output, this was a vector, right? And the reason was everybody goes to one neuron, right? Now it's getting replaced with one matrix, right? because we are computing a vector z, as much as classes we have, right? And then the next thing is that we are not doing the sigmoid activation anymore or entry-wise activation. We are doing a vector activation, right? And now, once we are at the output, then we can define a sort of loss and compute this loss, right? Okay, now, here in this forward pass, so this guy is quite basic. If I just want to do this, I mean, this is basically the higher dimension. This guy is now a vector activation, which is quite different from what we had before, because we used to have like every single guy passing through his own activation, but now we have all of them passing all together through one vector activation, right? So this is one key difference that we have here. Basically the only difference that we have here, right? And then the last thing is that we want to just backpropagate over this. So for forward pass, everything is quite obvious. So just multiplication, multiply, get the z value and activate it. Again, multiply, get the z activated. Multiply, get the z and activate it by a softmax. The only difference, right? This is the only thing that you need to do. And now, the next thing is that we check how we can move backward, right? And now, if I want to move backward, one last thing that I didn't mention here is the guy here, the loss function, which is going to look at my output y3 and now give me one loss value, right? This is something that I have not yet defined for you, right? But look at this problem that we have it on the board. I told you that, for instance, here we have 3 classes, right? So the output of this neural network, it's going to be a vector of size 3, right? What is your true label then? You can write it, but what is the true label that you have in your data set? This one is scalar, which is either 1, 2, or 3, right? It's going to say you are in class 1, class 2, or class 3, right? Now, you want to look at this vector of size 3 and then compare it to this one number. How we can do this, right? So this is the next thing we want to do. So I want to just get one vector of size, say in general, c, which is the output of my neural network, and I want to compare it to one true label. And say my true label is, for instance, v, okay? Now, this is the output of my neural network, right? It's going to be c different probabilities. So instead of y, I can basically write it down as probabilities, right? The first output of the neural network is telling me what is the chance of belonging to class 1, right? The second one is telling me what is the chance of being class 2, and so on till the last one. Now, if you remember with the binary case, we just looked at that true label as a probability. So we want to just do the same thing here. Okay? Now, let's say that I have image B, and this VB is one number between 1 and C, right? So it's, for example, 3. So it says that my image B belongs to class 3. Then, what is the chance of, what is the probability of my image belonging to class 1? What is the probability of it belonging to class 2? 0. What is the probability of it belonging to class 3? 1. Any other class? 0, right? So you're going to simply say that the chance of this guy is 0, next guy is 0. The true label, the chance of belonging to this one is 1. The rest of them are again 0, right? You're again going to end up with one vector. This is exactly of the same dimension, the number of classes that you have. And it's going to be non-negative between 0 and 1, every single entry. And if you add them up, they are going to be 1, right? So it is one probability vector. It's going to tell you that the chance of being this image belonging to class VB, it is going to be 1. Belonging to any other class, it is going to be 0, which is obvious because you do know the true class, right? Now, this vector has only 1, 1, and lots of zeros, right? This is what we call it one hot vector. You might have heard of it, right? So this is what we call it one hot vector. So this guy is a c-dimensional vector. C is the number of classes. Like if you have 10 classes, it's going to be 10-dimensional vector. And it's going to be 0 everywhere, but in one entry. And that entry is the entry that belongs to your true label, right? So if your image really is a handwritten 0, then this vector is going to have 1 at the first entry and 0 everywhere else, right? Clear? This is what we call it one hot vector, and this is how I'm going to show it from now on. So this bold 1 is a vector, and this is going to be 0 everywhere, but at the index v. Okay? Now, let's try one example together. Assume C is 3. Okay? Let me just do it here. Say C equals by 3. Okay? Now, what is 1? 1. What is it? Can you tell me? 1, because the index is 1. 1, 0, 0, right? What is 1, 2? 0, 1, 0. So you got the idea, right? So this is the example. So if C is 3, then, 1, 1 is basically first guy 1, everybody 0. 1, 2, the second guy 1. 1, 3, third guy 1, right? Everybody's clear, right? So now you have your true label. This is exactly one probability vector of dimension C. Your output is again a vector of dimension C. And you want to compare these two guys against each other. How you can do it? Just go ahead. You can use cross entropy. We need to just extend the definition. Or we can use MSE, right? Mean squared error, right? So again, if you want to just compare these two, so if you want to define the loss, which compares the output y3 against the one hot vector that you have, the true label that you have, you are basically comparing two probability vectors. And you can do it as before. So you can just go for a squared error, which is the good one. But the best one, which we usually use, is going to be cross entropy, right? Now, the squared one is basically the norm between these two, right? So you get these two vectors, your one hot vector and your output of the neural network. You just subtract every single entry, right? You make each of them a squared, and then you sum them up, right? So it's going to be basically y, the probability of every class, minus the true probability of every class, right? But this true probability of every class is going to be 1 exactly on the true class and 0 everywhere else, right? So you can more easily write it down in this form, right? So it's going to be y squared for every class which is not the true class. So you're going to get the probability of computed by your neural network squared for every class that is not a true class. And for your particular class, which is the true class, you are going to minus it from 1, minus 1, subtract it from 1, and then square it, right? And can you compute the gradient for this guy? If I want to compute gradient, what should I do? I should compute the gradient with respect to y. Great. So can you compute the gradient with respect to y? Yes, you can do it, right? This is just a square term, right? It's very easy to do it. You just need to compute the partial derivative with respect to every single y, right? Every single entry of y. So the partial derivative with respect to, for instance, y1, if 1 is not the true class, say v is not 1, then it's going to be 2 times y1, right? Class 2, it's going to be 2 times y2, and so on, till you get to class v, right? It's going to be 2 times y of that class minus 1, and for the rest of them is again the same, right? And you can more easily write it down in this form. It's going to be 2, your real output of the neural network minus the one hot vector. Easy fizzy lemon squeezy, right? So I learned it a few days ago from my kid. So everything fine, right? Okay. Now, what about the cross entropy? How can I define the cross entropy here now? So what did we do when we were doing cross entropy? Do you remember with the binary case? In the binary case, when the true label is 1, what is the cross entropy? If the true label is 1, if V is 1. So my true label is either 1 or 0, right? And then we said y3 is the chance of this guy happening, right? Now, the output, y, the value you compute by your sigmoid. And when this is y, how do you compute the cross entropy? What is it? Logarithm of 1 over, what was it here? Y, exactly. So in that case, you had just one scalar y, and then when your true label is 1, you're going to say logarithm of 1 over y, right? Now, what if it was 0? How do you compute the cross entropy then? Logarithm of 1 divided by 1 minus y, right? This was your cross entropy. Now, what is this guy? This is probability of being 1, right? Probability of class 1, right? What is this guy? Probability of class 0 or class 2, right? So I'm going to call it class 1, class 1, class 2, and then this is probability of class 1, 1 over logarithm of 1 over probability of class 1, logarithm of 1 over probability of class 2. Now if I have 10 classes, what should I do? It's going to be a logarithm of 1 over probability of the true class, right? So you're going to define it exactly in this form. So I have this particular expression for you written, which means that you're going to get the true probability vector, that one hot vector. You multiply every single entry of this guy with your logarithm of, you see minus here, so it is basically logarithm of 1 over that y, okay? And then you sum it up. But you do know that your one hot vector has only one, right? Everything else is 0. So when you open it up, this is going to be minus logarithm of y of the true class, right? So if you know your true class is 3, then your cross entropy is simply logarithm of 1 over the third output of your neural network, right? Everybody's clear? Yes? So now, anybody had information theory course or anything related? Don't be shy. Nobody? Why? Everybody, you should study information theory. This is very important. I mean, you really need to know why we do this. So this logarithm of 1 over 1 probability, this is what we call it in information theory, information content. Okay? The less probability something has, the higher would be the information, right? So if something does not happen really, so in the middle of winter in Toronto, you don't expect to see plus 40 degrees. If that happened, this is a very rare thing, right? Low probability. Then the news is going to say it, right? Because this is a very unlikely thing, so it has lots of information, news is going to report it, right? Less probability going to have more information. So this expression that you are computing is the information content of that particular output. So you know that the true label is 3, right? You're going to compute the information content of the distribution you see at the output. And you want that information content to be very small. Why? Because you shouldn't wonder that this is the true label, right? So this is, say, information theoretic viewpoint on that, but forget about it if you have not heard of this. Just give you as a kind of extra funny hint. Okay? Everybody's clear? So this is going to be the cross entropy, and now again, can I compute the gradient of this guy with respect to y? I can do it, right? So say that v, the true label that you see here, that is 3. What is the partial derivative of this guy with respect to y1? 0. y2, y3, minus 1 over y3, y4, 0 again, and so on, right? So you're going to see something like this, right? Correct? So for every other guy who is not the true label, the derivative is 0 because this guy is not showing up here. For this guy, the derivative is going to be minus 1 over that y, right? And then you can simply, again, write it down in terms of the 1-hot vector. Yeah? So the derivative is basically 1-hot vector, right? And you have derivative. You have the gradient. Okay, great. So we do know what is the loss now, and we do know that we can compute the gradient. So this means that when we started with a forward pass and we passed everything forward and we computed the loss, then we are going to have the gradient of the loss with respect to the output. That's going to be easy for us, right? And now, if I want to just do backward propagation, what should I do next? Please don't think about the dimension and details. Just give me the intuitive answer. Derivative of? Softmax, exactly. So you need to compute the gradient of y3 with respect to z3. And then again, the gradient of z3 with respect to y2. y2 with respect to z2, and so on, right? So you need to just move backward over softmax. We don't know it yet. We're going to learn it in a few minutes. Okay? After that, you just need to move backward to this guy. So basically, we have done it. Again, this is going to be the transpose of the matrix. We need to move backward from y2 to z2. Can we do that? Can we move backward from y2 to z2? Look at it here. Yes, this is entry-wise operation. We talked about this before. So we can do it. We need to move from z2 to y1. Again, we can do it as a linear operation. We do know how to handle it. And finally, we need to just move from y1 to z1. Again, we know it. Yeah? Everything in this architecture we do know how to do, right? The only thing that we don't know is this softmax, right? If we do know how we can backpropagate over softmax, then this chain is going to be complete, right? Everybody's clear? Any questions? No question? So just let's have 5 minutes break, and then we see how we can deal with softmax, right? Yeah, I think it was not like probably consider like this.
I guess like we did some stuff with Boltzmann's, but like it wasn't.
Oh, yeah,
it wasn't like it was way smaller. But anyway, like I was saying, I actually wrote out the stuff like you were saying and shot it, and I guess what I did was I just wrote it into there, and that was the easiest form to write it into the partial derivatives.
Yes.
And then I guess I was wondering was how do I combine them properly into making sort of doing the this function. Like you see what I did?
Yes, I think, but
I feel
why
like
you don't have the summation over I?
Oh wait, I should include the summation.
Yeah, if you include it, then you can write it in terms of one matrix giving another.
Okay. That makes more sense. I was like, I was like, all right, I have the 2 over I. There's no I currently.
deep
as
learning, yes.
maybe choose CNN or an
Yeah, anything that you want, right? So any application you have in mind, you want to do classification or even more advanced problem, you just can select one of them and try to accomplish it. So usually you need to have some predefined project, like define a project already been done, and then you are interested, you want to just replicate it or you want to just do it another way. So this is totally fine, right?
So it's like we submitted this week with how many topics did you submit to you and how soon approval?
How many topics? Just one topic.
Oh, just one.
Yeah, one topic, and the proposal should be like 200.
In that class?
So we just explained that this is the ideal, this is what we want. For instance, we want to train a model to generate image of
What?
Do we send you an email?
No, I'm curious. I'm going to open it like an assignment and then submit it.
When is it due? Is it due next 4.0?
No, I mean, I probably open it on week 5.
Okay.
But I'm going to leave it for 1 or 2 weeks.
Okay. Is there like specific format we should be following for the
Yeah, 200 words.
just 200 words, no format?
No, and then you make a flyer for it.
Okay. Okay.
should we start with the topic first, get the approval?
Oh no, you submit a proposal. If there is any issue with your, I mean, the topic, definitely what you suggest is okay. The point is that there might be one topic which you see like you cannot, it doesn't sound like feasible topic for you to accomplish what you want in this term. Then we're going to give you a hint cap. This is not going to be feasible, and then you might change it. So the whole purpose is that you have already one topic, so we make sure this is a feasible thing. So, but it's not like you're not allowed to do something. You're allowed to do anything.
All you had to do is just like the process.
What will be the difficulties, or it's what we are choosing?
I mean, if it shouldn't be like super duper simple things. So you don't need to do amnesty classification, which you told in your assignment, but anything more advanced than that one, this is okay. So if you, classic thing is that you see a pre-implemented project and you try to do it by your own.
Okay.
You know, this is totally fine. Yeah.
So we just need to implement a model for one program. We don't need to design several models and compare them all the findings.
No, you don't need. So
We
if
find the baseline.
yes, but if you need a baseline, then usually the work that you are I mean, you put your project baseline has a bunch of baselines, right? So you don't need to replicate the baseline anymore. You can take the baseline directly from that project. You only replicate the main solution, and then you compare whether you can. I mean, if you have it pre-implemented, then your baseline gonna be the result of that project, right? So you're gonna see whether you can fit to that. And sometimes it's even challenging to get to reproduce one already available result.
So we can use the result from others' work as our baseline.
Definitely. No worries. Yeah. You wanted to ask me something?
I submitted the group thingy, but I don't see like the group on the grid.
It hadn't been made into a group. So
No.
when did you do it?
So we did it last week.
Last week, right? A few days ago, I think.
No, a few days ago. Yeah. So right now.
No, not here. If you go to the people, or you don't have it.
Something like almost.
Okay, after the lecture, I can check if they
Okay.
have a group.
Right, yeah.
Essentially, you should have a group. So it might be that the PA forgot to just make the people here.
Okay.
And then when you click, then you have a group, and all of you are here. And then when you want to submit, one of them submits it, then you do a submission.
Okay. What is so the proposal
Flyer.
flyer? Let's do that.
I open it next week.
So you will be.
Yeah, that is the time that I put it on.
Okay. So it'll be not the time if you.
No, it's not.
Because I was very concerned. Yeah, because you haven't put it up. I was like, is it too weak?
No, it's okay.
Okay.
No worries on that.
Okay.
But I'm going to send you a person.
For sure.
Yeah. So I'm going to, when I'm back in the office, I will check with the team to see what.
So all the deadlines that I thought were deadlines are actually the start dates, not the end
The
dates.
second row is start date, the third one is deadline.
Well, in the there's.
Oh, for the project, I didn't put any deadline in this.
Okay.
I didn't say when I posted it.
Yeah.
It was my but I post when I open it, I post them rather than definitely there will be at least 2 weeks.
Okay, sounds good.
So one more thing I want to confirm, based on other people who've taken this in the past, a random topic.
Project, yes. So I told the team it's posted. I assumed that they did it, but they have not done it. I'm sorry. So I checked with them 2 days ago. They said like it's over because I saw it was a Google. So I'm gonna do it.
I just wanted to know if it existed or.
Yeah, it exists. We already made it, so I'm gonna post it.
Good, thank you. I kind of forgot how we got here. What are the
Because this is just y1, right? So when you take the derivative with respect to y1, it's 0, right? Say these three.
Oh, yeah, so we only have one number.
One number.
Thank you.
Okay. Okay, yeah. Yeah, okay, I'm gonna check, but have you tried to check on the option? Okay, if you didn't find anything with me, then I'm gonna let you know. I mean, you still have time, you can do it, so there's no rush on that, but please do it by the next week. Oof. Shall we go on? I mean, it was like far more than 5 minutes. So, yeah, back propagation through the vector activation. So we want to now move backward over the softmax, right? So how can we do this? So I want to just get back through softmax. And one thing that you should do always when you get into a new operation, that this is going to, I mean, if you do deep learning, this is going to be for you forever. Like everybody comes with one new operation, they have a new idea. So if you instead of doing this, you do that. If instead of a normal convolutional layer, you just put in inception layer, then it's going to do better. Then the key question is that how I can move backward through that. Because at the end of the day, I want to train it and I need gradient, right? And you can always do it exactly the way that we did it with the local operations, right? So you can just break down, just prune everything, just look at the single branch that you want to do back propagation over, right? So here, for instance, what I can say that with respect to softmax, the whole story, or any vector activation, the whole story is that I have one, say, c-dimensional vector z, and then I compute one vector activation, I get into y, and then from y, I compute the loss, right? Now, I am able to compute the gradient of the loss with respect to y. The question is that how I can compute the gradient of loss with respect to z in terms of this function, this vector activation, and the gradient that I do already have. Okay? This is the question now, right? If I do know how to handle this problem, then I can backpropagate over the original architecture I showed you, right? So let's do it. Now, before I go on with this one, let me just try one thing for you here. So say I have had C different classes, right? So this means that when I compute my Z vector, Z is going to have C different entries, right? So my Z is going to be Z1, Z2, till ZC, right? And then I am going to compute out of this with vector activation Y1, Y2, till YC. Now, if I look at Y1 only, so say I am looking only at Y1. I'm just looking at this one. Y1 is a function of, say I'm showing this function by this f, so it's a different from that f. It's a function of, what do I should write here? What are the variables that make y? Is it a function of z1? Think of softmax. Is it a function of z1? The first probability, is it a function of z1? Yes. So z1 is here. Is it a function of z2? Yeah, the z2 is also here. Is it a function of z3? And so on. Is it a function of zc? So everybody's here, right? So if I want to do chain rule, this is going to be a vectorized form of chain rule. It's not a simple entry-wise chain rule anymore, right? So let's look at it together. So if we want to do that, we basically need to define the notion of Jacobian. And the notion of Jacobian is exactly defined in this form. Because if I consider this y, and I compute, and I want to compute the derivative of y1, what kind of derivative do I have? Do I have a simple scalar derivative, or I do have a gradient? I'm going to have a gradient, right? So I'm going to have the gradient of y1 because y1 has partial derivative with respect to z1. It has partial derivative with respect to z2, and so on, right? So it's going to have partial derivative with respect to every single guy inside this, right? Because it depends on all of them, correct? So y1 has a gradient, right? What about y2? The same. It's going to have a gradient. Is this gradient the same as the gradient of y1? Not necessarily. It's different, right? What about y3? Same. And so on. So you have a vector of outputs, and every single of them has a gradient, right? So if you put all of these gradient vectors together, you're going to make a matrix, right? That matrix is what we call it the Jacobian, right? So you have a vector output, you have a vector input. Now your gradient is going to be of the form of a matrix, and this is what you call it Jacobian, right? So this is how we look at it. So the function f is a c-dimensional function, c to c-dimensional function. So it's going to get this whole input, z1 to zc, and it's going to compute the whole output for you. And now every single body, every single yj is going to have one whole gradient, right? And now if you just collect all of these gradients together, you're going to end up with one matrix, which we call it the Jacobian matrix. So the Jacobian matrix is basically the collection of those gradients. So the first row in this matrix is collecting the gradient of the first entry. So y1 is here. Now you can compute the derivative of this one with respect to every single z. And you do it, and you write it down in the first row. y2 is the second entry. Again, you can compute the gradient or derivative of this guy with respect to all different entries of z. So you're going to do it and write it down in the second row, and so on till the last row. Now, what is the dimension of this matrix? How many rows does it have? C. How many columns does it have? C. It's C by C, right? So, yeah, exactly. Jacobian is to be dimension of the output times input, always, right? Everybody's clear what the Jacobian is? Okay, great. Now, let's now get backward over this guy. And to do this, I just write you one chain rule, and then everything going to get clear for you. So you don't need to look at the board right now. Just look at what I do on the, not on this slide. Just look at the board. So I want to compute the partial derivative of r hat with respect to, say, z1. So I want to compute the partial derivative of my r hat, this error term here, this loss term here, with respect to the first entry here. Okay? Now, if I want to do it, so I would write it down by chain rule to be the partial derivative of r hat, say with respect to the first y1. Then what should I do? I should multiply it to what? Exactly. So partial derivative of r hat with respect to z1, it's going to be partial derivative of r hat with respect to y1 times partial derivative of y1 with respect to z1, right? Should I stop? No, because not only y1 is a function of z1, y2 is also a function of z1, right? So I'm going to write it down as plus partial derivative of r hat with respect to y2 times partial derivative of y2 with respect to z1. Should I stop? What next? y3, right? y4, and so on until I end up with all entries that I have, right? This is the vectorized chain rule. So I'm going to keep doing it till I am ending up with the last guy. So it's going to be the last one is partial derivative of r hat with respect to yc times partial derivative of partial derivative of yc with respect to z1. And this summation, this whole summation is going to be my first partial derivative, right? So this is exactly what you have in this slide. So partial derivative of r hat with respect to any entry zc is going to be the partial derivative of r hat with respect to y1 times partial derivative of y1 with respect to that z, right? Plus partial derivative with respect to y2 times derivative of y2 with respect to that z, and so on till you end up with all entries in y, right? So this is basically the vectorized chain rule. And if you write it down, now you tell me if I remove these guys here. So I am just removing this one. I am removing this one as well. And I am removing this one as well. Okay? Now, I have partial derivative of y1 with respect to z1. Partial derivative of y2 with respect to z1. Partial derivative of yc with respect to z1. Where can I find these entries? First row or first column? First column, but right. This is going to be one of the columns, the first column of your Jacobian matrix. Okay? So you can simply see that this is basically this term. I mean, you can open it up. This is an inner product of column C of your Jacobian matrix times the gradient of r hat with respect to y. Okay? So you basically get one of those columns in your Jacobian matrix, and you inner product it with your gradient that you already have. And then if you again sort it out, as we did before, just to fix the dimensions, you're going to see at the end that the gradient, okay, I think I again forgot one equal sign here, so it's going to be gradient of r hat with respect to z equals to. It's going to be the transpose of your Jacobian times your already available gradient. Okay? So again, what you need to do when you are moving backward, just you need to compute the Jacobian. And can you compute the Jacobian? Can you? Yes. I mean, Jacobian, you define softmax by your own. You can write down every single partial derivative. You can put them in form of a matrix. And whenever the value of z is known to you, you put it inside that matrix. You're going to get the exact Jacobian matrix, right? Transpose it, multiply it with the gradient that you had from the next layer. And then this is going to be the gradient of the next layer, right? The previous layer. So moral of the story, when you want to move backward through one vector activation, you just need to do transpose of Jacobian. Okay? Now, if you are not interested, you can stop listening to me for a few seconds. But if instead of defining that entry-wise product, I would have looked at those entry-wise operation again in this form, then I would have ended up with the same form, but my Jacobian in this case, when the function operates entry-wise, is going to be diagonal. And when you do that diagonal operation, it is exactly like doing entry-wise product. Okay? If you are interested, just when you're home, try it. Okay? Just think of that entry-wise function operation to be a vector function, because that is a special case, right? And then you try to write it down in this form. You see that your Jacobian is diagonal, And then when you multiply that Jacobian into the previous gradient, it's like you do entry-wise product. Okay? But if you didn't get what I said, just forget about it. That's totally fine. I know it's like quite abstract. Quite fast to say. Okay, everybody's clear? Okay. Great, so we do know how we can move backward. Moral of the story, whenever we want to move backward, we just need to compute the Jacobian, and that's going to do the backward propagation for us. And now everything is over in this chain, right? So I do know how to do this. Then here I just need to compute the Jacobian, put it here, and then everything else is as before. So if I have a multi-class classifier working by softmax, then I can do forward pass, and I can do backward pass, meaning that I can compute gradient, meaning that I can use gradient descent, meaning that I can train this network. Problem solved. Clear? Everybody's okay? Any questions? No questions? Great. So if you got no question, then let me just wrap up everything in this form of algorithm. So this is the gradient descent. Now we have W1, W2, W3. I mean, in the initial form, we had it a vector because at the output we had just one sigmoid. Now we have a multi-class classifier. This means that we have a matrix. This is the matrix which computes Z for us, and then it's given to the softmax, right? And then we're going to start with some initial value, and now we know how we can forward and backward move on this graph. So we're going to get every single data, move forward, compute every single value in between. And then once we're at the output, we're going to just move backward, and then we're going to get a bunch of sample gradients. Okay? And now we're going to do it for all the data samples that we have. And finally, we just average those gradients. This is going to be the gradient of the empirical risk, and we are going to update our weights. No? That is the gradient descent, right? So, any questions? Everybody's happy with this multi-class classification? Yes? B is the index of your data. So you have capital B different data points, different samples. So you have, say, you have 1,000 images, so 1, 2, 3 to 1,000. Yeah. The whole data set for now, right? It converges. But you're going to see that we need to just make it lighter because this is not really feasible in practice. But the idea up to this point is exactly the one you said, right? Okay? So, any questions? No questions? Great. So, if you got no question, then this is what we call it full batch gradient descent. Yeah? And full batch gradient descent is pretty much something that you pretty much do never in deep learning. Yeah? So, what do I mean by that? By full batch? So, batch in this course means the whole data that you have for training. Okay? I do know that some of you have background on deep learning, and for you, batch is the small guy which you take from the data set, but that is for me mini batch here. Okay? So batch is the whole data that you have, the whole training data set. It's fine if you use different terminology, but just don't get confused when I talk about batch. So batch is the whole data that you have reserved it for training. And if you just want to do this, this means that you need, I mean, each time you want, if you want to do this algorithm here, this means that each time you want to update your weights, just one step of gradient descent, you need to loop over the whole batch of data completely, right? Go forward, backward for every single of them, which is a huge thing, okay? It's a huge burden on your computation resource. Now, some of you might ask me, because I have not mentioned it explicitly right up to this point, that what do you mean by having training data? Do we have anything else? Isn't that exactly the whole data that we have? So as we're going to see at the end of this chapter, no, it's not the whole data. So if you have a data set, you're not going to use all of it for training. Because if you do that, then you are left with no new data to just test your model, right? So if you do it on this data, how you can say whether if you get a new data, this is going to work fine or not, right? So the trick is that we usually break it into two parts. One part is the part we take for training. So I get this part, I'm going to do the training on this, and I don't look at the other data. So that remaining data is totally new to my network, right? And once I did the training, I'm going to give those new data into it, and then I see the output and I check with the true label. If they are the same, then I say, okay, the training has been gone well. If they are not the same, then it could be underfitting, it could be overfitting, things like that we are going to talk about later, okay? So the key point here is that usually when we talk about a batch, this means the amount of data that we collect to just do the training. A rule of thumb, say you keep 80% for training of the data you have, of the samples, and 20% maybe you leave it for test, later test, okay? Now, if you have 100 data samples, then your batch, the full batch that you have, and you think of 80-20% split, then 80 samples is the whole batch that you have, okay? Now, you might wonder how big this could be and how hard this could be to do in practice if I want to do the training, okay? So let's look at a few public data sets. So there are a bunch of things. I mentioned it a couple of times, MNIST in the lecture. So there are a bunch of data sets, which we call them public data sets, meaning that there have been a bunch of people that just wanted to do research on same things that we are doing right now. And they just needed a bit of samples and data to just do the test on them, experiments on them. And then they started to collect data. They just formed them in a very good format, so good data structure. All of the data had been annotated, things like that. So, for instance, in the case of MNIST, so there had been a bunch of people in Princeton, about 1.5 or maybe 2 decades ago, and they wanted to do just this image classification at that point of time. And what they did, they basically started to collect those images of handwritten digits. And each of them, they were just labeling it. So they were scanning the image, making it into 28 by 28 pixel, and then they're right in front of it, the label is 0, right? And then they collected it, and they called it Modified National Institute of Standard and Technology, MNIST, okay? Because it had been done there, okay? And this is not the only data set. This is the simplest data set you can find. There are lots of public data sets on the internet. For example, C410, C400. You might have heard of it. It's the Canadian data set. So C410, 10 different objects, cat, dog, bird, I don't know, car, airplane, 10 different objects, images of those objects in resolution 32 by 32 with the label. So label 0 or label 1 is, I don't know, cat, for instance. Label 2 is dog, and so on, right? 10 different objects. C400 is the same thing, but 100 objects, okay? So much larger data set. There are also other ones like ImageNet. This is something that we talk about in Chapter 5. So this was the data set they did to just, it had 1,000 classes, and they did it basically for a kind of image classification challenge at some point. And AlexNet from UofT could just win 2012, which started the whole stream of deep learning, and the wave of deep learning started from that. Or we have the data set Caltech 101, Caltech 256, and then Fashion MNIST is a newer version of MNIST, where you have, again, small dimension images, but they are, instead of handwritten digits, they are fashion. They are different clothings, okay? And they are all labeled. So at the end of the day, I mean, you can always find them online. At the end of the day, when you do a practice, when you come up with one idea, you say, I think this is going to work better, you always need a data set to just test on this data set. And we try a couple of them in this course in your assignments. Probably you get in touch with some of them in your project, but there is a sea of them out there. And I mean, nowadays, if you do research, one of the key points is that you just give your experiments working on very challenging data sets, okay? So These data sets you can always access through PyTorch, so you really don't need to download images of MNIST and then import them into your Python code and then you just transform it into pixels and in terms of vector and so on. No, you just you read Torch Vision, so you import Torch Vision and then you go inside dataset module and then you read MNIST and it's going to download everything and it directly downloads it in form of tensors, right? So life got easier nowadays. You can just simply do it. Old days, people had to just do it by hand, right? But nowadays, we do it directly. So now, in the example of MNIST, as I told you, the images are 28 by 28, and the labels are simply 0 to 9, but you have other sort of data set as well. But now, how many images, what is the size of data set that we have in MNIST, okay? In MNIST, you have 70K different images, okay? And this 70K is equally distributed between all digits, right? So it's going to be 7,000 zeros, 7,001, 7,002, and so on, right? But from this 70,000, we typically keep 10,000 for test, and we're going to use 60,000, so our whole batch of data contains 60,000 samples. Each of them is one image, 20 by 8 by 28, which is going to be 784-dimensional vector pixel, right? And this is one sample input, and the label, so 0, 1, 2, till 9. Yeah? You have 60,000 of that, okay? And now, let's say that, for instance, you want to just do this. So your whole batch of data is now 60,000 for training, 60,000 images, and you need to just do, if you want to do one step of gradient descent, you need to do 60,000 forward pass, backward pass, right? And you compute 60,000 different gradients, and then you average all of them. Now you have your gradient, and you can update once, right? Now again, you need to repeat it. And this doesn't sound to be very feasible, right? I mean, even with nowadays computers, even in this simple data set, it could potentially take quite some time, right? So if you want to do this full batch training, then you basically need to do 60K different forward and backward pass in every single step or iteration of your gradient descent, which is not really feasible. If you want to just have a rule of thumb, so you can just, I mean, in general, you're going to be, say, you need to have 100 iterations till your gradient descent somehow converges. Then this means that in total, you're going to just do 6 million forward and backward pass over this, this architecture, right? And even if each of them takes, I don't know, a fraction of second, millisecond, this is still going to be a large training time for MNIST, something that you can do it quite fast nowadays, right? So this is, at the end of the day, not the case that we do. I mean, if we have a larger data, if we have a very deep architecture, then this is practically impossible to be done. And the thing that we do with, we just come up with some sort of alternative idea that still is doing gradient descent, but it's doing it with less complexity. And this is what we call it nowadays a stochastic mini batch gradient descent. Okay? Now, the mini batch, I put it in the brackets because usually people don't say mini batch anymore. They simply say a stochastic gradient descent, even though stochastic gradient descent is a bit different. We're going to see both of them, right? But the whole idea now is that you do know how to compute gradient. You do know that gradient descent is going to just solve your problem. The whole issue is that you're not willing to do this much of forward-backward pass in every single iteration, right? So you don't want to do that. And the thing that you want is to just see how you can resolve it. The first idea people came up with was the idea of sample level training. What does it mean what do I mean by sample level training? So this is your gradient descent, right? So you're going to start with a bunch of ways, then you start to iterate, right? Look at line 3. And when you are iterating, you are going to just do one forward pass, one backward pass, and then you're going to get a bunch of gradients, right? So in the full batch training, what do? I'm going to keep this gradient, and go for the next sample, right? I compute that one, go for the next sample, I compute that one, and so on until I'm over with the whole batch, right? And then I average it. But people said, like, why should we do that? Why don't we update right away when we have one sample gradient? Huh? It is still gradient, right? So I can still get this sample gradient, GB, this particular gradient of my weight, and I update my weight with this guy. So this is the gradient I computed after one single forward-backward pass, right? And I replace it here, okay? Now, I start with the same data, so I start with the first data, and then I do one forward-backward pass. I have something which is a gradient. This is not the gradient of the empirical risk that I want, but it is the gradient of one sample error, right? One sample loss. I forget about that, I just update, okay? I go for this next data. I do one forward-backward pass. Again, I get a sample gradient. I forget that this is a sample gradient. I update, okay? And I keep on going. And if I get over the whole data and the training is over, I stop. If I do it and the whole data set is over, so I just went for the first data sample, second till the last one in the batch, and I see that everything is over, but the algorithm has not converged yet, what I'm going to do, I'm going to get back to the first one. I repeat this, okay? So this is what I'm going to do this. So whenever I exceed the batch size, I again update b equal by 1. So I'm going to start with the first one, second one, third one, till the 60th one in MNIST. And then I see my weights have not converged yet, so I'm going to get back to the first image again. And I repeat this. So people said, maybe we can do this, right? What is the issue with doing it? And if you do that, I mean, with the trick of stochasticity, then it's going to work. It's going to work, okay? So this is the whole idea of sample level training. I call it sample level training. I'm not sure if it's a kind of, say, universal terminology. I just made it up by myself, but it sounds like something rational to call it sample level. But by sample level training, it simply means that when you're training, you don't wait for the whole batch of data to get over, right? You just compute one gradient, and whenever you have a gradient, you use that opportunity and then you update, right? And you hope that your weight is going to update much faster as compared to do lots of full batch training iterations, okay? Because if you do this, when the whole batch of data is over, you have done, for instance, in MNIST, 60,000 updates, right? Whereas in MNIST, in full batch training, you do 60,000 forward, backward, and then you do just one update, right? So you're much ahead of this. And how bad your gradient could get, right? This was the idea. Okay, so this is the idea of sample level training. So you might come up with this question that this is actually not the standard gradient descent that we talked about, because when we are taking the gradient, we are not really, we are not updating with the gradient of the empirical risk itself, but we are updating with the gradient of one of the terms inside that empirical risk, which doesn't sound the same thing, right? But basically, people look at it as a kind of approximative gradient descent. And the whole reason is that the true full batch training that we are doing is indeed itself also an approximative approach. Why? So let me just give you one short description of this. And I promise this is going to be short, but it's going to help you a lot when you see in future any argument about stochastic gradient descent or any stochastic form of gradient-based algorithm. So one ideal scenario. So say I do the first sample, so my first data point, I do forward pass, backward pass, I end up with one gradient. And I call it gradient 1. Okay, this is the first gradient. Then I do the second forward, backward pass, I end up with gradient 2, right? So I'm going to call it G2, and so on until the last one in the batch. Say when I do in the full batch training, if I do forward, backward, B times, all of them turn out to be the same. Then, how do I update in the full batch training? I'm going to get all of these guys and average them. What is the average of these guys? Every single one, right? So if I want to just do this update, it's basically the first gradient I computed, right? So the second one is exactly like the first one. The third one is exactly like the two second ones, the two first ones. So you're going to see that I'm just waiting for nothing, right? So I could have updated with G1, and then I saved lots of time, right? Correct? So this is the idea. So if I could somehow think of that, this thing happening, then this sample-wise training is basically the full batch training that we are doing right now, right? I don't need to wait the whole full batch, right? If that ideal case is happening, like every single gradient is the same, then doing it every sample is equivalent to doing it every complete batch, right? What is happening in practice is that you are not going to compute exactly the same thing. So this equality is not happening. But you can think of every single of those gradients that you are computing as one ground truth gradient. So there exists one ground truth gradient. And every single gradient that you're computing in a forward-backward pass is one noisy sample of that. Meaning that it's that guy plus some noise, right? And this noise is sometimes increasing the gradient, sometimes decreasing the gradient, right? And when you have lots of them, like in the full batch gradient, they are going to average out, and the noise impact is going to get less and less, right? Yeah, I'm going to repeat it in the next slide. So what you can think always of every single sample gradient that you are computing, that it is one ground truth gradient. There exists one gradient in the Mars, not on the Earth, okay? In the Mars. None of us know it. But that gradient exists, and whatever you see, whatever you compute in every forward-backward iteration is a noisy version of that. So that guy plus some noise, right? Now, if this is the case, and if the noise is very, very small, then it's fine enough that you update with your first sample, right? You don't need to wait the whole time, because waiting the whole time is going to just remove the impact of that noise, okay? So this is the idea. The idea is that when this noise is very small, then you could say every single of those samples that you are computing the gradient is exactly an approximation of this guy. And indeed, what you compute as the average of all of those sample gradients is again an approximation. Because the average of all of those sample gradients is not going to be exactly the gradient that is in the Mars, right? We are still not getting that. Now, given that we discussed about this risk and empirical risk before, do you know what is that gradient in the Mars? I mean, if you can say it, I mean, I don't expect that you immediately get it. I do, just as a hint. But if you can say it, then it's going to be super duper great achievement for me. So you remember that initially when we wanted to train, we wanted to minimize the risk, right? But we couldn't compute the risk. So we said, okay, we just compute an estimator of risk, which was the empirical risk, right? Now, what is that gradient in Mars that we don't have access to? Gradient of risk, the true risk that you don't have access to, right? And the gradient of the empirical risk that you are computing is an approximator of that guy. Gradient of every sample loss you compute is again an approximate of that one. Okay? All of them are approximating this. The key difference is that this guy, sample gradient, is not approximating very well. This one is approximating better. So your sample gradient is an approximation of your very true gradient that you do not have access to. Very bad approximation, very high noise. Your full batch is a better approximation of that one, but it is not that one. It's only an estimator of that. Okay? Now, yeah, so moral of the story is that every single gradient that you compute in one forward-backward iteration, forward-backward pass is going to be one estimator of the true gradient you really want to have to update your model perfectly with. But when you do full batch training, this estimator is going to be better, so it has less error. When you are doing sample-wise training, it's going to have high error. But the question is how much time you want to spend to get a better approximation, because sometimes better approximation is not going to do you a lot. Okay? So this is the story. So the story of a sample-wise gradient. And I'm going to just talk about it a bit next session more. So I'm going to give you a bit of more sensing about this trade-off between having good quality approximation in very high, in the full batch case, and low quality estimation in the case of sample level. But for the moment, just take it from my side that every single gradient you are computing in forward, backward pass is just one noisy sample of the gradient you want. And as long as that noise is acceptable, you can just use it to just update. Okay? But one last thing before we finish this lecture. That is the behavior that we call it repetitive cycle issue inside sample level training. So what is the idea here? The idea is that if you do sample level training that I told you, exactly the way that I told you, like start from the first one, second one, so on till the last one, then again you get back exactly at the first one. Then you might get into a kind of behavior which is cyclic. And this cyclic behavior could stop your algorithm from converging. So how this can be, how you can think about this. So I am just giving you one very dummy example here. So say I am doing update. So I start with some initial weight, W0. And then I use this sample level training and I go for my whole batch of data. So I first start with my first sample and I update. I'm going to get to W1. Okay? This is the new update, right? After you just go forward, backward, you compute a gradient, you update your weight, right? This is W1. Then I go for the next data sample, then I get W2, W3, and so on till I get to the last guy. So second sample is going to give me W2 till I get to WB. So this is the very last guy, okay? This is the one which I get after updating with the last data point, okay? Now say my algorithm has not converged. What should I do? Go back, right? But what's going to happen if this last update that I got here is exactly the same thing that I started with, W0? I'm going to repeat, right? So if I started with W0 and I ended up with W0 itself, when I get back again at the beginning of the data set, I'm going to repeat the same cycle, right? So I update the same thing, end up with the same weight, and I go back. And it doesn't matter how many times I go over my data set, I am not going to converge, right? Correct? So this is a kind of cyclic issue that is problematic. How we can rid of it? Any idea? Exactly. So why should I start exactly with the same data point? Before I want to start again, I just shuffle everything, right? If I shuffle everything and again I start, then the point that I start with is not the same point, the first sample that I started last time, right? And then this means that now I could have different updates, right? And hopefully I'm going to get into some convergence. This is the idea that we call it a stochastic gradient descent. That's it. It's not anything weird. It's stochastic because each time before I update, I'm just doing a shuffling. This shuffling makes the start point randomly, right? This is a still gradient descent. It is sample level, so I'm just using one sample gradient each time. But I start with the stochastic point, and the main reason is that I don't want to see this cyclic behavior. So you just loop over the batch every time. If you do this in this case, it's not going to help. The only simple fix to that one is to just go for a stochastic gradient descent. So each time that you want to start with your batch again, you're going to just shuffle this batch of data all, so that the sorting of the data points get randomly changed, and then you start again with your data set. Okay? This is what we call it SGD, and SGD is the most common algorithm nowadays people use, like as the basic thing. And any other algorithm that we have is basically working based on SGD. Okay, so this is going to be the whole idea of SGD, and I think random shuffling is quite obvious to you. What do I mean by random shuffling? It means you just randomly exchange the place of the data samples, right? And then this is going to be SGD. So you basically do exactly as before. So